So our first speaker is our invited talk. We have Jiadong Zhang, who received their PhD in 2012 from Fudan University and was at a postdoc at Johns Hopkins University before joining the University of New Hampshire, where he is now a professor. His research mainly focuses on theoretical condensed matter physics with a focus on magnetism. And today they will present on the magnetic Hopfion, a three-dimensional topological spin texture. So that I can hand it over if you'd like to share your screen.
Okay, thank you for introduction and thank you for having me. So so today I'll talk about the magnetic Hopfions. It's a new topological spin textures in three dimensions, and it has attracted a lot of attentions recently. So before my talk, I like to I was asked to pass around this message. So right now there's a call for nomination for the IUPAP Early Career Scientist Prize in the field of magnetism, and this is one of the most prestigious award in this field. So if you know someone that fit the criteria, please go ahead with the nomination. So I will talk about the topological aspect of spin textures, and topological aspect can be traced back to the topology of a magnetosphere. So here the spins are lying in three dimensions. So there are two topologically different structures. One is spin polarized, and the other is the hedgehog on the right. So if you place this hedgehog configuration on top of 2D plane, and for any point on the plane, you draw a line connecting to the North Pole, and this line would intersect with the unit sphere. And so if you give the spin at this intersection to that on the 2D plane, so as if kind of you project the hedgehog configuration onto a 2D plane, what you get is the new skyrmion, and this new skyrmion has been discussed a lot in like magnetic multi-layers. But if we rotate all the spins about z-axis by angle of 90 degrees, you get block skyrmion, and that has been observed in some bulk materials, the chiral magnets. So that means there is a interesting duality between a unit sphere in 3D to a texture in 2D. Right, so a unit sphere is a hedgehog configuration. It's a defect in 3D. So and then the corresponding texture in 2D is a skyrmion. So if we generalize this duality, we reduce the dimension by 1 on each side. And what we get is a duality between a defect in 2D and a texture in 1 dimensions. And this defect in 2D is just a vortex. And that the texture in 1D is actually a domain wall. So there is a duality between them. So if we raise all the dimensions by 1 instead, and we should get a defect in 4D and a texture in 3D. And this texture in 3D is what I'm going to talk about today. It's the Hopfion. So this skyrmion, again, we start with skyrmion. For skyrmion, we constructed in the by the stereographic projection that I just mentioned. So if the point on 2D plane has a coordinate of x, y, and then the line connecting to North Pole intersect a point P with the coordinate n1, n2, n3, and this can be expressed by this equation. So if R is infinite and n3 is pointing up, and if R is 0, n3 here is -1, it's the spin is pointing down. So this literally describes a skyrmion configuration in 2 dimensions. And as I said, I want to generalize it, and we can escalate the dimension by 1. So we can easily get a map from a point in 3 dimensions to a point in S3. S3 is a unit sphere in 4 dimensions. What we do is just to keep the first 2 terms fixed and keep the last term and make up a new term that replacing x or y by z. But what we want is a spin configuration, and a spin lives in S2, right? It's the spin, if it's normalized, it is lives in a unit sphere in 3 dimensions. So what we need to do is just to use the quantum mechanics. So what we do is given these four numbers, psi1, psi2, psi3, psi4, and we make up this spin law. And then we calculate its expectation value with respect to three Pauli matrices, and we get three numbers. And these are the three components of the spin. And in this construction, we can get a Hopfion configuration like this. And these are the distribution of some typical spins. So this is a very complicated three-dimensional distribution of the spin, actually. As a topological structure, there is a topological index. And for the hedgehog that I just mentioned, and topological index is very simple. It's just the total solar angle expanded by this by the spins. And this solar angle can be written in terms of the sine theta, d theta, d phi. And for skyrmions, this theta and phi depending on the coordinate in coordinate x and y. So we do the variable substitution, and we eventually end up with this nice expression, what we call a topological chart that has been observed in terms of a topological effect, for example. And this a topological chart can be expressed in terms of component of nx of n's. Okay? So it is the total antisymmetrization of IJK three indices and total antisymmetrization of two derivatives, partial mu and partial nu. Okay? And this is actually a integral of the emergent magnetic field, and it is this magnetic field that caused the topological effect that has been observed in many experiments. So what about the topological index of Hopfion? So what we do is just to, again, to generalize what we have for skyrmions. And what we do is just to total antisymmetrize all the components of psi and total antisymmetrize all the derivatives. And we can get this topological index. And this topological index can actually be written as the integral of B dot A. Here, B is the emergent magnetic field. It's generalization of the emergent magnetic field of the skyrmion in 3 dimensions. And A is a vector, it's a vector potential associated to B. And this is a very complicated expression, but it has a very interesting geometrical meaning. A spin configuration is regarded as a map, right, from 3 dimensions to S2, the spin space. Right? But we can inverse this map for any specific spin direction, and we can ask where in 3 dimensions on which the spin is pointing on that direction. Okay? And this equal spin contour would be a closed loop for the Hopfion. Okay? So for example, if we want to find all spins pointing along x direction and minus x direction, right? And we get 2 closed contours. And on red, all spins pointing along x. Okay? And on blue, all spins pointing along minus x. And these 2 closed loops are actually linked to each other. And if you want to find more, this linking number is actually this topological index that I mentioned. So if you want to find more per-images associated to other direction of spin, and eventually you see that all the spins with 0 z component and will form a torus plane. And on this torus, all these spins has vanishing z component. Okay? And this is what I mean by this nice picture to represent the Hopfion. Okay? So that means there is actually very interesting relation between the skyrmion and the Hopfion. So what you need to do is just to, maybe I should, is there a pointer? I don't know how to get a pointer. Anyway, okay. So if we take a series of cross sections of the Hopfion, and what we get is a series of skyrmion configurations, and it's the helicity of skyrmion that is changing while you're taking different cross sections. So that means if you start with a skyrmion tube, okay, like here, if you twist it by angle of 2 pi, then connect 2 ends, you will get a Hopfion configuration. And if you take a cross section on the XY plane of the torus of this Hopfion, what you get is a target skyrmion. So this is a center skyrmion wrapped by a spherical, a circular helical stripe. And if you take a cross section along the YZ plane, and what you get is a pair of skyrmion and anti-skyrmion. So that means if you image the Hopfion in different directions, you'll get completely different image, no matter you're doing it in terms of X-ray or Lorentz transmission electron microscope. So back in 2018, we made the first theoretical prediction of magnetic Hopfions. Because I'm from the skyrmion background, and we know that for a chiromagnetic nanodisk, for example, iron germanium nanodisk, with a proper radius and thickness, there will be target skyrmion stabilized inside. So our prediction is to put this nanodisk in between two spin polarized layers, and then there will be a nucleation of the Hopfion inside. And this prediction was later experimentally realized by Peter Fisher's group. And what they did is to have a stacking sequence of magnetic multi-layers. By fine-tuning this sequence, they can get the chiromagnet in the interior and the spin polarized, the large perpendicular magnetic anisotropy layers on the top and the bottom. And there is a good indication of the Hopfions inside. And later, there were also some other predictions, and actually, there were also some experimental observations of the Hopfions in chiromagnets. Like on the left panel, Tokura group from Riken, they observed the Hopfions in iron germanium. But Hopfions in this setting is not complete, and they call it a fractional Hopfion. On the right up, and this was a recent paper, a Lorentz transmission electron microscope, again on iron germanium. And they saw this very interesting patterns, and the theoretical calculations support that it is some strings of skyrmions wrapped by a Hopfion. And also there are other theoretical predictions of designing some notch and then send current, and the skyrmion will be created. So recently, in collaboration with a group from High Magnetic Field Laboratory in China, we made the first unequivocal Hopfion observations in iron germanium. So what we do is to send a current, give a pulse of a current. And the ground state in iron germanium is helix. But after the pulse and the system relax, and then there will be a Hopfion nucleated. And you can see that from the Lorentz transmission electron microscope, and here I actually used electron holography, and send electron beams in different directions, and you get different patterns. It's a transition, a crossover from a skyrmion anti-skyrmion pair all the way to the target skyrmion by tuning the direction of the electron beam. And the experimental observation is nicely consistent with the simulations. So this proves that this is indeed a magnetic Hopfion. And given the Hopfion, we are also interested in its dynamics. In early work, we simulated this LG equation with the spin transfer torque and with the non-adiabatic spin transfer torque as well. And then we send a current, and this Hopfion would move. And this, interestingly, if we apply a current along x direction, the Hopfion acquires a velocity in both y and z direction. And the torus plane of the Hopfion is also rotating. So this is the case with beta. The parameter for the non-adiabatic spin transfer torque is larger than alpha, the Gilbert damping. So if we have another parameter with beta larger than alpha. And again, this Hopfion acquires the Hall velocity and the torus plane rotates, but the direction of both are actually opposite of the previous case. And in a very special case, when this alpha equals to beta, and by sending the same current, this Hopfion moves straight without any rotation and without any Hall effect. So this numerical simulation can actually be captured nicely by an analytical analysis. So what we do is to model the Hopfion motion, the collective motion of the Hopfion, and write the spin at the time and the spatial evolution of spin in terms of this equation. Here, capital R describes the displacement of the Hopfion, and this theta, the parameter theta in the rotation operator O, describes the rotation angle. Then we plug into that AlG equation, and we can write the term on the left in terms of this collective coordinates. And then we use the similar theta approach. But in standard theta approach, we usually apply this term on both hand side and then integrate over. But the meaning of this term is actually give you the linear momentum, because in the past we are only interested, for example, the collective motion of the domain walls. Right? So we care about the linear momentum. But right now we are talking about Hopfion, a three-dimensional object, and we're interested in rotation and three-dimensional motion. Okay, so we like to generalize this theta equation by applying this term on both hand side of the AlG equation as well, and this gives you the angular momentum. And as a result, we end up with this equation motion for the Hopfion, and the result of this one is nicely consistent with the numerical simulation. What about experiment? So this is the experiment, right? And we show that by sending a current pulse, and the Hopfions is indeed moving along the current. Right? And there are also more to explore in this direction. And if you compare the velocity of the Hopfion with that of the skyrmion, you can see that it even has a large slope. So that means given the same current, the Hopfion will move faster than the skyrmion. And also you can design some interesting structures, and you can move the Hopfion by current, okay, from any point in 3 dimensions to another point in 3 dimensions. So this is indeed a building block for a 3-dimensional logic devices. So far, we only talk about the individual Hopfion. Okay? And from the fundamental physics aspect, we are also interested in the realization of the Hopfion crystal. And actually, there is a way to construct a Hopfion crystal that we recently developed. So this is the way. And for Hopfions, this is what we used to construct that. But actually, we can develop some intermediate steps in between. What we do is, instead of mapping directly from S3 to S2, we can map S3 to a complex number. Right? Then map the complex number to S2. And what we do is, we call this psi1 plus I psi2 Z naught, and psi3 plus I psi4 Z1. Okay, so these are two complex numbers. Then I can construct another complex number as a fraction of polynomials of Z1 and Z naught. And then, given this complex number, we can construct a spin direction, nx, ny, and nz by this equation. And actually, my previous construction correspond to the simplest choice of psi, that is just the Z1 over Z naught. And if you do this math, and you will see that this is exactly this torus-like Hopfion that I constructed. But the beauty of this approach is it can give you some high topological index Hopfion structures. Right? So for example, if you choose this kind of psi values, and you can get very interesting knot structures of the Hopfions. Right? So this still gives you one Hopfion. But what we do is we embed this S3, right, for psi 1, psi 2, psi 3, psi 4, these 4 numbers in 4 dimensions. And then we write this psi as a superposition of some multi-Q states. And then in this construction, we can end up with a Hopfion lattice. But then the next question is, can we make up a model that stabilizes this Hopfion crystal? And the answer is yes. And what we did is to study this very simple frustrated magnet model. Okay. So this is J1, J2 model, for example. Okay. J1 is antiferromagnetic, J2 is ferromagnetic coupling. So there is a frustration. Okay. And if you do the continuum limit, and this Hamiltonian will describe the energy function of this model. And we show that this Hopfion crystal can actually be a metastable state for this model. And we indeed get a simple cubic lattice of the Hopfion that is stabilized in this model. Okay. So then it opens up a door for more theoretical and studies. For example, we can study the magnon excitations and many other interesting phenomena. Okay. But the most important important value of this analysis is to give you a way, okay, to find or to discover new materials that could possibly stabilize a Hopfion crystal. And so the Hopfion is interesting, but we are still seeing that there are a lot of challenges in this in the Hopfion, or generally speaking, in the 3-dimensional topological spintronics. So one challenge is the image. So in magnetism, we have a lot of different ways of imaging magnetic configurations, like MOC, MFM, or spin polarized STM. Okay. But all these techniques can only give you the distribution of magnetizations on a 2D plane, right, or projection onto the 2D plane. But in order to confirm a Hopfion configuration or any other interesting 3-dimensional configurations, we literally need to know the spin distribution point by point in 3 dimensions. And recently, we are seeing the development of X-ray magnetic tomography. Send X-ray into different directions through the sample, okay? And then optimize the cost the loss function, okay? End up with the reconstruction. Okay? And on the right hand side, we also developed a counterpart in terms of electron holography. It is the electron beam that goes through the sample in different directions, then optimizing the configuration, and we will end up with a reconstruction of 3-dimensional spin distributions. But we are also interested in some other more advanced technique of reconstructing 3-dimensional magnetic distributions. So here we use some deep learning techniques. Right? So the way we reconstruct a 3-dimensional configuration is similar as taking the pictures of a transparent object in different directions, okay, and ask you what is the 3-dimensional object is. Okay? So we use some existing deep learning method and applied it in this magnet setting, and we really see very good performance. And this can also give us the reconstruction with very small numbers of angles that going through the sample. So I see that I only have 1 minute remaining, and I like to talk about another interesting challenge related to this 3-dimensional topological spin textures. Okay. As I said, eventually we want to find some more interesting materials realizing the Hopfion configurations. But finding new magnetic materials is challenging. Okay. In the past years, we have witnessed the rise of machine learning technique. And if there is a large database, we can predict new magnetic materials. But for the magnetic community, we are seeing the lack of a large magnetic database. For example, there are some database materials project, Airflow, but they're from computations. And sometimes the DFT calculation doesn't give you the correct magnetic information like Curie temperature or new temperatures. On the right-hand side, we have the Bilbao Megadata. It is a very high-quality database of magnetic materials, but they're also they're from experimental observations. But the problem is they only have less than 2,000 entries. So what we did in the past is we take advantage of the literacy of large language model and extract this data from experimental papers. Okay. We convert a PDF to we convert this PDF to text. Then we feed this text to large language model and extract the correct information. This information would include the chemical information, the chemical formula, the structure information, and all the magnetic information that we need. And then eventually we build a database that is open to public. So if you're looking for new magnetic materials, given whatever criteria you want, and you can find these materials in our database. And our database right now consists of more than 60,000 materials. And we also have database for superconductors and thermoelectric materials. And we also want the whole community to contribute to this database. So there's a button here, contribute. So you can just upload your paper or any experimental notebook to this one. And the data will be collected in our database and open to the whole public. And your credibility, you will be also acknowledged for these contributions. Okay. So yeah, and with this database, we can also train some simple larger models and predict some new ferromagnetic materials with high Curie temperatures. Okay. So I hope that this can can address some challenges in this community. Okay. So with this, I will skip the conclusion and thank you for your attention.
Thank you very much, Professor Zhang. It was a really interesting talk and such a great overview. I think we have a little bit of time for questions still, and we have one currently in the chat, which is from Sonia, who's asking a bit more, asking about what is the application of these Hopfions.
Yeah, for the application, as I said, we can use this Hopfion for three-dimensional logic devices, because this is as far as I see, is the first true three-dimensional topological entity, three-dimensional magnetic entity. Okay. In the past, we have, like, for example, the block points. Okay. So this is like a hedgehog, but block points actually very difficult to move. But Hopfion, as you can see, that it moves very easily by controlling the current direction and current amplitude.
Thank you. I believe, Galen, you have your hand raised.
Yeah, I have a quick question about the current-driven dynamics of the Hopfions.
Yeah.
So you show that there's sort of three different types of ways it can move. It can rotate the torus either forwards or backwards or not at all. Do you guys predict different velocities or sort of coherence lengths for the Hopfions based on this rotation?
The velocity So I don't quite get your point. So what do you mean by coherence length?
I guess I'm thinking of sort of like when you're moving a domain wall or like a skyrmion, you have a coherence length. Do you have a similar, like, for how long the Hopfion sort of stays in path? Or is it
Yeah.
not?
Okay. Yeah. So here are the thing. So there is actually a upper limit for the distance that this Hopfion can move in our simulation. The point is this torus plane would rotate, right, as you apply the current. And so eventually this torus plane would be perpendicular to the current direction. And then if you further increase if you further keep the current on, and this Hopfion would expand or gradually shrink. And we don't know whether this is numerical instability or it is the true fact. But at least from our analytical analysis, it appears the expansion of the Hopfion is possible. Yeah. But of course, we don't have any dissipation channel in our simulation. With the dissipation channel, if there's the expansion of the Hopfion will be paused, then probably this Hopfion would move with fairly long distance without being destroyed.
Right. Thank you very much, Professor Zhang. I think we have to move to the next speaker, but if everyone could please thank our first speaker again. Thank you very much.
Thank you.